All right, so in this example, we have another idea of something that is both rotating and moving and whether or not it's slipping. And we're going to kind of analyze this through a different view. So the other one, we just said, hey, it wasn't slipping from the beginning. In this one, there is slippage to start. So we're starting with a bowling ball. That should be a bowling ball of mass m and radius r. Notice that we're not given m and r, and as we get further into the problem, it gives us actual numbers. So that's a key to me almost immediately that as I go through, these two things should cancel out. But anyways, we have our bowling ball. We're going to assume that it's uniform because it doesn't say otherwise. Is thrown horizontally immediately on the floor with a speed of 5 meters per second, and it is not rotating to start. So I can go ahead and just start my information here. I know to begin that v is equal to 5 meters per second, and because it's not rotating, I know that omega is equal to 0 radians per second. It gives us a coefficient of kinetic friction. We know that if you're sliding, you're skidding, there's going to be that kinetic friction. And because the kinetic friction is away from that center of mass, it is going to cause a torque. So we're going to look at that too. So here we have it as 0.08. And I think that's all the information it gives us to start. So the very first thing it wants to know is for how long does it skid? Until it starts rolling without slipping. So once again, we have this key information. We know that if we're rolling without slipping, that means V is equal to R omega. So we're trying to figure out how long does it take to get here. So this is going to be our end constraint. If these are our beginning constraints, this is going to be our end constraint. We're going to use that to work together. So because I'm starting with some initial velocity, I'm ending with some other velocity, I know that there needs to be acceleration. So the first thing I'm going to do is I'm going to start with a force equation. I'm going to say F equals ma. Here I know that my force is friction, and that's going to be mu. My normal force is going to be mg, and that is going to be equal to ma. I can cross out my m's, and I get that my acceleration of my center of mass, the acceleration of the ball itself, is equal to mu g. Now that I have an acceleration, I can try to use some kinematics. I know that V final is equal to V initial plus AT. My V final is going to be R omega because that's my end restraint. My V initial was 5, and my A is mu G, and there's some time. Well, looking here, my problem's asking me to solve for time. I know mu, I know G. R has to cancel out, and I don't know omega yet. So I know that I still need to get R to cancel out somehow, and I have this omega here. So I'm going to take a pause, and I'm going to look at this through the scope of rotation now, because I didn't have everything I needed when looking at it translationally. So through the scope of rotation, I'm going to do torques. Torque is equal to I alpha, which is equal to our force, which once again is mu mg, and then its distance away, which is R. Now, in this case, once again, because it's a bowling ball, we're assuming that it's a perfect uniform sphere. We're going to say our I is 2/5 mr squared. For now, because I am actually trying to get an expression for omega, I'm going to leave alpha as alpha. I can cancel some things. I see that my m's cancel on either side, and I see that one of my r's cancels out. So that gives me an expression that alpha is going to be equal to 5 mu g over 2r. Just like I did with the kind of translational linear, I then use kinematics. I'm going to do the same thing here. And I'm going to say that omega final is equal to omega initial plus alpha t. Here, this represents my omega final because I'm trying to get to this area. So this is what I'm actually trying to get. I'm trying to get an expression for this omega final. My initial omega was 0. My alpha, we just found, is 5 mu g over 2r, and then time. Well, time's what I'm trying to solve for, and I have time here, so this is actually okay. I'm ready to substitute it in. So now I'm going to take this phrase and substitute it in here. So I'm going to get R instead of omega. I'm going to write 5 mu g over 2r t is equal to 5 minus mu g t. So I took my two kinematic equations, my one from translational, my one from rotation, and I put them together with the understanding that after this same time, this is my expression for omega, and at this point, omega r will be equal to my velocity. So that's what I'm trying to find, is what time makes this statement true. As I come to solve this out, I see that my r's cancel. So now I have 5 halves mu gt equals 5 minus mu gt. I have this bit here, which I know can be similar to each other. In order to get rid of this, I'm just going to multiply everything by 2 because I think it's make it slightly easier. So that gives me 5 mu gt equals 10 minus 2 mu gt. I'm going to add that over. So I get 7 mu gt equals 10. T is equal to 10 over 7 mu g. And at this point, I have all of this information. Mu is given. I know what g is. And if we plug all of this in, we get that our time is equal to approximately 1.8 seconds. So we were able to tackle this by understanding what were our initial constraints, what is our final constraint, so understanding what does it mean to be slipping and not, and it's not slipping when this statement is true. And then I looked at it through the scope of translation and the scope of rotation, and I was able to put those two kinematic equations together in order to solve for my time. Now that you have time, I'm not going to solve it all the way out, but you could go ahead and find the distance using delta x equals v naught t plus 1/2 at squared. We have time now. You are given v naught, and we have an expression for your acceleration over here. So you can plug those all in, and if you want, you should get 7.8 meters.